All right, we're going to work through an exam style question asking about average rates. So we're working in chapter 14 on kinetics. And in this question, we're given a balanced equation for the combustion of ethane. And then we're given some data that was collected on this reaction. So first off, make sure that you're sort of paying attention to what data is given to us. We have time, and then at those time points, we're collecting concentrations of carbon dioxide. So that's one of our products. And so we're generating that as this reaction proceeds. So our first question here is asking for the average rate of appearance of CO2 over the entire experiment. All right, so we have to just do some reading comprehension here and say they're asking for the whole experiment, so all over the whole time. So from 0 to 18 seconds. So for this first question, I'm going to say my average rate of appearance, and I'm reading this as being from 0 to 18 seconds. All right, so that'll be, I guess we'll do this. Our change in CO2 is a function of change in time. And so at this final time point, I have 0.21 molar. I started with none of it, and I'll divide it by 18 seconds. And we'll wind up with, hopefully, the answer. All right, so I got 0.012 molar per second. So on average, that's how much CO2 we produced over that whole 18 seconds, right? But of course, that is an average. If I'm going to plot this, it should look something like this. Okay, so here's, well, by that I mean like this, okay, because we're producing it. So this is constant time and concentration of CO2, right? So it's increasing from 0 to 6. We had a big jump from 6 to 12. It was another jump, but smaller, and then it keeps getting smaller because we have less reactant to create product. So this is happening because we're consuming reactant, and the rate depends on the concentration of the reactant. So what we gain here from this is that from 0 to 18, we have made 0.21. So essentially we're looking at this slope, right? That's our average rate of production over that time period. But of course, it's faster here at the beginning and it's slower here at the end. If we were looking at shorter time chunks for the average rate, or if we were looking at instantaneous rates of reaction. Okay, so I have 0.012 for this one. The slowest rate of appearance of CO2 during the experiment was, and then you get some answers here or some options. All right, so in that options, we have the instantaneous rate at 0 seconds. Okay, that's going to be our fastest production. Right, because we are generating the most, and then we want to know when the slowest is. So that's going to be at the end here, where we have basically the reaction has stopped, so we're not producing anymore. So I would say that this is going to be our slowest rate of production. That instantaneous rate at 18 seconds. Okay, you have some other options, the average rate from 0 to 18, or which would be what we just calculated. Okay, so that is definitely steeper than what we have here, right? Basically, I'm just thinking about like how big is this slope. So this is the smallest slope. It's much smaller than 0 to 18 because in that 0 to 18, we are including all of this increase here, right? And then 12 to 18 would be the next, if I was, had to rate these, 12, the average rate, which is the last option from 12 to 18 seconds, would be slower than the instantaneous rate at 0 and the average rate from 0 to 18, but it is not slower than this exact point right here. Okay, so we would be looking at like, if this was 12 to 18, that would be our average there. Okay, it still is waiting time points that have a faster rate. So this is instantaneous at 18 seconds. Okay. The average rate of appearance of water from 0 to 6 seconds was. All right, so this is an interesting question. It's multi-step. We need to first get the rate of CO2 production, the average rate from 0 to 6, and then we can translate that into production of H2O using our stoichiometric ratio, or if you want to think about it in terms of the average rate equation, either one is fine, but let's start with this. Delta CO2 is going to be 0.10 minus 0 divided by 6. This is in molar, this is in seconds. Okay, so we have 0.1 divided by 6. That's 0.017 molar per second in that same time frame. So we could think about that as molar, where the moles in that molar are CO2. Right? I don't want CO2. I'm looking for the answer in terms of water. So I could just grab my coefficients here and say, well, for every 4 moles of CO2, I must have also produced 6 moles of H2O. Okay, so I'll multiply by 6 divided by 4. That gives me 0.025 or 6. If we're rounding, and this is now in terms of water. Okay, I like this approach better than the average rate equation. It makes more sense to me, but you'll get the same answer regardless. And the average rate equation I'm talking about is what we brought up in class today. We said average rate, and in this case, it would be, if we wanted to write this whole thing out, which I don't really want to, but let's be thorough. Okay, so our disappearance or consumption of ethane has this 2 here. I'm grabbing, right? We're going to put our stoichiometric coefficients in the denominator in front of that. This is negative because this is going to be a negative number, and we want to set this equal to production rates as well. So here's what I would have for oxygen. Here's what I have for the production of CO2. Here's what I have for the production of water. All right, and so I'm grabbing those coefficients. What we solved for in the first part, this 0.017, that was this, okay? And I wanted to solve for this. So I multiplied by 6. So there's our 6/4 ratio to tell me that the change, the appearance of H2O over that first 6 seconds was 0.026 molar per second.